Hi everyone, in this video we'll see how you can create and deploy your first smart contract on the Solana blockchain. We'll be writing the smart contract in Rust and deploy it on the local net that we have, and then we'll write some JavaScript code to actually interact with the program. A quick recap. A few videos ago we saw that if you want your program to be able to store data across transactions, this data is actually stored into an account itself. So the program that we'll be writing right now will store some data on the blockchain, and this data will be stored in an account that the user has to pass to the program. So if there are multiple users who will be interacting with this smart contract, each one of them will have an associated data account for this program. The program that we're writing is a very simple program. This is the Hello World program that's provided by the Solana folks. What it lets you do is it lets you maintain a counter on the chain and increment the value of this counter as you interact with the program. So the program will have logic to increment the value of counter for an account that is passed to it. So if a user wants to interact with the program, they'll first need to create an account and send some lamp ports to it, because this account will actually have some space. And in order to have an account that has some data on the blockchain, you have to pay rent. Once it has created this account, it will pass this account to this program, and the program will have logic and access to increment the value of this counter by 1. Now you might be asking, how will this program have access to change the data inside this account? The reason for this is that when we're creating this account, we will actually mark the program as the owner of this account. And an owner of an account actually has access to modify the data inside it. So the users are effectively providing you with an account and hoping that your program does what it says it does, which in this case is it will increase the value of the data inside this account by 1. So now let's try to get into the code and see how they do it. So this first smart contract that I shared with you is actually the example Hello World smart contract that Solana provides. The code of this resides in this repo that I'll have linked in the description down below. Let's first clone this code locally and try to go through it. This serves as a pretty good boilerplate code for writing smart contract and also interacting with it, but later we'll see how you can create your own smart contract from scratch. There are also a few prerequisites to this. You'll need to have Rust installed locally, but if you've been following the examples up until this point and you've installed the Solana CLI locally, you most probably already have Rust in your machine. So with that, let's clone this locally. And let's open this inside a text editor. The first thing you need to do is install a few local dependencies. You can do that by running npm install. While that is happening, let's try to see what all source code exists here. So if you look at the source folder, there are 3 folders in here: client, program C, and program Rust. A smart contract on the Solana blockchain can actually be written in both C as well as Rust, but we'll be writing it in Rust. So let's open the source folder in here, and there's a single file here called lib.rs. Let's open that up and explore it. So at the top of the file, there are a few imports. The first one is from a library called Bosch. Without getting too much into it, the Bosch library actually lets you serialize and deserialize basic data like string into a more complex format like binary. Then there are a few imports from the Solana program crate that we'll be using later on. The first thing that's done here is that we've defined a struct. The struct is similar to a struct in C++, or you could think of it like a class in Java, although it doesn't have inheritance properties. Rust is not object-oriented, so it doesn't have a concept of classes, but if you want to group data together and have some functions on top of it, you can use structs in Rust. So this basically defines the structure of your data, and you can create variables of this type, which will basically in this case have a counter attribute, which will be a 32-bit integer. This line basically exports the program and will be present in any smart contract that you've written, and the function that you're passing to it will contain the actual logic of your smart contract. So this basically is the meat of this program. Let's try to understand what arguments it gets and what it does inside it. So the first argument to this program is the program ID. So whenever this function executes, this will be present on chain. And as you remember, everything on the Solana blockchain is an account. So this smart contract will also be deployed in an account, and the program ID basically represents the public key of that. The second argument here is an array of accounts. So as you remember, all data on the Solana blockchain is actually an account. And most of the times when you're calling a smart contract, you basically need to operate on that data. Now, since that data is present in an account, this accounts array basically provides a way for you to specify what all accounts this smart contract needs access to, what all accounts it might access, what all accounts it might change the data for, and so on. The reason for this is that providing these accounts upfront makes the Solana blockchain faster, because anytime this instruction will run, the node that is running it will be able to know upfront what all accounts it needs and will be able to bring them in memory. Lastly, there's something called as instruction data. Now, when you want to call a smart contract, generally you want it to do multiple things, not just one. And instruction data basically provides the client who's calling the smart contract a way to pass in custom data to the program. So if you're building, let's say, a calculator, whether or not you're running a addition or a subtraction transaction would lie here in this instruction data. So think of this whole thing as a function, and instruction data being the actual set of parameters that the client provides based on which the smart contract does different things. So if you've worked with functions before, this might look slightly weird. Like, why are we restricting ourselves to just 3 arguments? Why is the second argument an array of accounts? Why can't I have a more custom set of arguments that I can pass to a function? The short answer here is that the fact that we're able to pass in accounts as an array is what fundamentally makes Solana faster. It expects you to be able to extract all the information that you need from this accounts array inside your smart contract. And if there's any other data that you need to pass it in this instruction data array. This is a U8 array, but it can be serialized into a custom struct. And then based on the contents of that struct, you can do various things inside your smart contract. Now let's actually dive into the smart contract. The message macro basically is a more efficient way to log anything inside a smart contract. You might have seen a println macro, but it's not as efficient as the message macro, which is why this is what we use when we want to log inside a smart contract. Line 30 is an interesting thing that you'll see across many smart contracts. As I mentioned, this accounts array basically contains a set of accounts that the smart contract needs access to or needs to change the data of. And this basically represents a way for you to iterate over all of these accounts. So when you call next account info on this iterator, it basically one by one provides you with all the accounts. So if we were passing multiple accounts to the smart contract, you would basically be able to access all the accounts one after the other by using next account info. Now it might happen in the future that you have 20 different accounts that you need to pass to a smart contract, and unfortunately this might look a little ugly, but this is the way that Solana expects you to extract these accounts. Now, if you remember, our smart contract basically lets users maintain a counter on the chain and then increment it by calling the smart contract. So the first thing that we're doing here is we're extracting the account and we're expecting the user to provide us with this account, which is the data account where their counter is stored and where they want to increment the counter. So that's passed in as an argument, and that's the only single account that's needed in this instruction. The next thing we do is we check if the owner of the account is this program ID or not. Now remember, the program ID, the variable here inside the smart contract, is the actual ID of the smart contract. So this might feel a little unintuitive when you're testing this locally. Basically, this program ID doesn't really have any existence. This program ID only makes sense once this program is deployed to the blockchain. And every time anyone calls this instruction, this program ID will be present as an argument. So on line 36, what we're doing is we're ensuring that the owner of the account, the data account that the user passed in as an argument here, is this program ID. Because if that's not the case, then this program won't be able to modify the data inside this account. And so if that's not the case, we basically return an error and we log out that the account that was being asked to be greeted, or the account where we wanted to increase the counter, isn't really owned by this program, and hence the program won't be able to change the data inside it, and we error out right here. If we don't add this check here, and a user submits a request where the account that they're passing in is not owned by this program will basically error out later on, because Solana won't let this program change the data inside the account that was passed. Finally, if this account is actually owned by this program, what we're doing in these 3 lines is we're first fetching the data from this account. So this account already might have some data. We're fetching that, and this try from slice will basically deserialize this data into the greeting accounts struct. So if you remember, this is the struct that we defined initially, and the structure basically contains a single counter right now. This is the variable which we will keep on incrementing as users keep on calling the smart contract. We deserialize the data that's present inside this account. We're increasing the counter by 1, and then we're resending that data to the blockchain. So what these 3 lines will do is they'll fetch the data, they'll increment the counter by 1, and then submit it back on the blockchain. And by the end of it, when this function ends, the data on that account, this account that the user passed in, has been modified. So taking a step back, what this whole program does is it lets users pass in an account. That account needs to be a data account that is owned by this smart contract, and it increments the value of a counter inside it. Now, since anyone can read any data on the Solana blockchain, once this counter is increased, you can actually read this value, or anyone can actually read this value and ensure that the counter is increased by 1. So this is the basic smart contract. Now let's try to deploy it on a local blockchain and then write some client-side code that can interact with it. The way to deploy this is fairly straightforward. You have to run npm run build program -rust, and this will actually convert this Rust file into the .so format. So this file has just been compiled right now. It doesn't yet exist on the Solana blockchain. To actually deploy it, you have to run this command that it spits out. Before you do that, you need to ensure that the Solana blockchain is running locally. So let's do that. And now that the Solana blockchain is running, let's try to deploy this program. So as you can see, there's no error and the command spit out a program ID. Let's try to explore what this looks like on the Solana Explorer. So I just opened this on the Solana Explorer, and as you can see, this is also an account, but this is a special kind of account called a programmable account. It has some executable data inside of it. And if you see here, it says upgradable yes, which means that I, the person who deployed this program or the person who is the authority of this program, can actually update the smart contract. And finally, it has a field called executable data, which again is a data account where the actual code of the smart contract is stored. So if I download this file, it will actually contain the compiled code. And as you can see, it has 0.84 Solana in it, which is a lot. But the reason for this is that this smart contract takes a lot of space, and hence we need to have some Solana in there to be rent exempt. So now that our program has been deployed on the Solana blockchain, let's write some client-side code to actually interact with it. So if you look at the client library inside this project, you'll actually find the client code that can interact with the smart contract. But there are a few extra things here. So I've tried to trim it down into a very minimal version that will basically do the same thing and interact with the smart contract that we've just deployed. So let's look into that. I've created a new folder called counter-client in the project that we were initially running our web3.js examples in. I have a single file here which basically contains all the code to interact with the smart contract. So let's try to go through it. The first thing that's present here is the program ID of the contract. So that's basically this thing right here. The second thing is a class as well as a map, which basically kind of contains the schema of this data that will be stored in the account. So if you see, this data is actually exactly the same as the data that's present in the Rust project. So if I go to the struct here, it has a counter variable, which is a 32-bit integer. And we have the same thing here defined in this schema. We also have this class that we'll see later on why we need. But basically this has a counter attribute and a very basic constructor that sets the counter. The main function that we'll be calling here is called call counter, which will basically call the smart contract. And we're passing in a new key pair, which is basically the account that will execute this transaction. It is not the data account. It is the parent account, or basically the person that wants to interact with the smart contract. So the first thing that the call counter function does is we airdrop some Solana into it, because since it needs to interact with the smart contract and also create like a data account, it needs some Solana. As you can see, I'm actually connecting to DevNet, and I've actually deployed the smart contract to DevNet as well, to be able to show you that this can actually work in a DevNet, and if you deploy this to the mainnet beta, it will work there as well. First thing we do after airdropping it some Solana is that we create a data account. Now, as I told you initially, that every person who wants to interact with this contract needs to have an associated data account, and that's what we do here. If you look at this function, it basically creates a new key pair. It sends the instruction to actually create the account using the system program. And there are a few extra things here. Up until this point, whenever we were initializing a new account, we were basically expecting the space there to be 0. And if that's the case, we could basically just send in 0 lamp ports and it will still initialize. But in our case, since this account needs to store some data, it needs to have some space. And the reason this is 4 is because that's what the structure will need, the structure that we're trying to store here. This kind of a schema actually needs 4 bytes. How can you calculate this number? If you go to the actual client-side code inside the Hello World example repo, you'll find logic to do that. I'll leave that as an exercise, but to remove any complication, I found that value and I'm hard coding that value inside this account. And we're also transferring some lamp ports to it, because since it needs to exist on the chain and have some data, it needs to have some lamp ports in it. We execute this transaction and wait for it to finish. And once that's complete, we have a data account where we can now call the smart contract, and the space that this data account has is basically the same as the space that the smart contract expects. We log both of these here so that we can play with these later on the Explorer. Now we have everything to interact with the smart contract, and that's exactly what we do next. We create an instruction to the program ID that exists on the chain. This is the program that we've just deployed. We hard-coded this value here in this variable. And if you remember, every instruction needs to have an array of accounts that it needs access to. In this case, the data account is the only account that's needed. So we pass in just the public key of that. We don't need to pass in the private key because this data account is actually owned by this program. How do we know that? Well, if you go to the top here, when we were creating this account, the program ID that we assigned here is the program ID of the contract. Now, up until this point, this was system program. So our accounts generally are owned by system programs, the accounts that we hold our Solana in. But if you want a data account and if you want a program to be able to modify the data inside it, the owner of that account actually needs to be the program that should be able to modify its data. So since we've done this here, this check that we added here, the account.owner is not equal to program ID, this will succeed because the account owner is equal to the program ID. That's exactly what we're doing on this line. The third thing here is the data. In this specific smart contract, the data doesn't really mean anything. This program doesn't need access to the data, but in the smart contracts to come, we'll pass in modified data here and see how that works with the smart contract. Finally, we send this to the smart contract and await for it to finish. And once that's done, we get the account info for this data account. It should now have the value of the counter as 1. And that's exactly what we try to confirm here. We deserialize this data into the greeting schema, which is something we defined earlier. And that's why we need the greeting account. The Borch.serialized client library basically lets you deserialize this data into a class based on the schema of this data. And finally, we confirm that the greeting.counter is actually 1. We log that and we'll be able to confirm that from our logs. So let's try to build this program and see what it spits out. So right off the bat, you can see the log states that this account has been greeted 1 time. And if you go to this account on the Explorer, you will be able to see that this account is actually owned by the smart contract that we were just calling it on. This is the program that we deployed initially. And it has 4 bytes of data and 1 Solana in it. Now anyone can actually access the data inside it and confirm that the value of this counter variable is 1. What do you think will happen if I call this smart contract again? If we said that the counter value here will become 2, you're actually wrong. And the reason for that is every time you call this program will actually end up creating a new data account, and starting from scratch, the value of it again will be 1. So let's modify this data so that it interacts with the same data account that was created when we ran this program the first time. So this is the data account that was created. Let's copy this and let's store this in the value of the data account. Also, let's try to comment out whatever we don't need. So that's pretty much it, I think. Now the data account is not really fetched from a new one. The data account is hard-coded to the value that we've created initially. So now that we've hard-coded this data account to be the public key that was basically generated the last time we ran this program, we will now be calling the smart contract on this data account that we've already created. The value of counter there is already 1. So let's see when we run this, does it get incremented by 1 and become 2? So as you can see, it spit out that this account has been greeted 2 times. So that's how you can deploy a smart contract and how other users can interact with it to store data on the Solana blockchain. This was a very simple smart contract and didn't really expect any arguments to it. But in the next one, we'll actually send in some data here, and based on that data, our smart contract will do different things. So let's get into that in the next video.